Hello, my name is Tyler Siddle, and I'm here today to present my senior technical project, which is the Kawiki HS1 headstock positioner. A little bit about Kawiki Aaronsons. They are a world leader in positioner and cutting machine technology. They specialize in headstock, tailstock, tilt, turn, and rotate style positioners. One thing that's really interesting about Kawiki is that everything that they do is made in-house and designed in-house. The idea for this project was to take the design from the sales order to maximize profit while maintaining an appealing and safe product. And also we needed to meet all customer parameters that are laid out in the sales order. So here is the actual sales order. This has everything that the customer wanted. From the mechanical side, the capacity for this headstock positioner needed to be 1,000 pounds with a center of gravity no more than 12 inches away from the face of the table. The machine needed to rotate at 0.3 to 6.5 RPM and no more than 3,000 pounds of torque. There was also a fixed height requirement that was originally stated that we ended up having to change later on, and just a few other small electrical specifications as well. So, some more product description. As I said, 1,000 pound capacity. They wanted a touchscreen display, portable pendant control, and a very compact and sleek design with a small footprint, and a 3-jaw chuck system as well. Here's my project timeline that laid out each step of the process for designing and then manufacturing the machine. The first was to determine constraints that the customer needed and wanted, then marketing and visual design, which was getting a baseline idea of what the machine would look like, then the initial design and everything that goes along with the initial design, which includes FEA and component review, design review with manufacturing, which is incredibly important to bounce ideas back and forth and to make the product as good as possible. Then cost analysis, finish the design work, and then manufacture the prototype. So to start with the finite element analysis, this is an extremely powerful tool for engineers to use that allows for safety, allows for a good product design that allows you to properly size the material as well as optimize the components so that they're not way overbuilt or they're way underbuilt. Now, Kawiki is a company standard on all lifting, positioners, and cutting machines where no member of the machine, structural member, can have a stress more than 12,000 PSI found in the analysis. So the first simulation that was run on the shaft, and it was to represent the force applied on the shaft by the key stock. The force applied was the 3,000 pounds of torque, and it resulted in a maximum stress of just under 2,700 PSI, which is to company standard. The next one was a remote load mass simulation applied on the shaft to represent the load felt by the shaft due to the 1,000 pound capacity. As you can see right here, this is where the load was placed and then where the shaft is fixtured on the rectangular tube. The resulting maximum stress was just under 8,400 PSI, which is also to company standard, and it shows that being within a few thousand PSI of that 12,000 mark, that it's starting to become very close at optimizing the shaft. Now on to engineering calculations. The first calculation that was completed was the key stock calculation. And this was to determine the length of the key stock given the width and height that we had already called out due to what was given to us by the gearbox or the shaft limitations. The calculated length of the key stock was 2 inches. The next one was to determine the maximum stress felt due to the torsion on the shaft, and it was found to be just under 2,000 PSI. So that means that the shaft is plenty strong enough for this application. The next calculation dealt with the bending stress felt by the rectangular tube, which is the main stand of the machine and the main base. So we used moment calculations to represent the load, the weight of the chuck, the weight of the motor, and where it pivots on the top of the rectangular tube. Now, the maximum stress determined from these calculations was just under 4,500 psi. So this means that the shaft is more than adequate enough to withstand the load felt on at the max load of the machine. The next engineering calculation was the weld calcs for the rectangular tube where it meets the base plate. As you can see here, it's just a very standard weld calculation with a resulting load of just over 500 pounds felt by the rectangular tube. With the relatively small load, the weld that was needed to hold the rectangular tube to the base plate is only a 1/4 inch weld all the way around the rectangular tube. The next calculation was for the thread engagement on the actual bolts that mount the base plate into the concrete. This is to ensure that when the machine is fully loaded, it won't tip and it won't pull it won't strip the threads on the lift or on the lugs that are concrete or anchored into the concrete. It ended up being a 1/2 inch grade 1 bolt with a 1/2 inch grade 1 nut, which is relatively small, but it is plenty adequate for this design. Now on to manufacturing and customer review. As you can see here, this is the rotary union that we ended up using for this machine to meet their purging needs. There was quite a bit of research done for this rotary union to ensure that it would meet the hose size that we need that allows for the correct volume of gas, and also that it would be compatible with the type of gas needed for all different types of welding, so that it wouldn't decay or corrode over time. Now on to cost analysis. The largest part of the cost analysis for this machine was the basic design of the machine. At Quickie, shop time, welding time, and machining time are very expensive. And so it is very critical that we make a very simple machine that does not allow for too much welding time, too much machining time, or anything like that. With this straight rectangular tube design, as we saw earlier, it's very overbuilt, it's plenty strong enough, but what it allows us to do is to take this rectangular tube, use the plasma, cut the hole, and then use very little machining time to machine this hole to the correct dimensions that allow the shaft to be put into this into the cylindrical hole. Also with the base plate, just a few gussets, very simple, very quick welding, takes very little time, so that this machine can get pushed through the shop very rapidly, which definitely minimizes costs, which brings the cost down for the customer and also maximizes profit for us. Now here is the prototype that was built and sold to the customer. As you can see here, we have the gearbox attached to the shaft that goes through the rectangular tube. Then that is attached to the electric motor, which has the specs called out in the sales order. And then on the bottom here, there is a brake as well. And then on the left here is the box that has all the electrical components inside. And you can see the rectangular tube design as well from that angle on the left-hand side. This is just another look at the machine after it has been all done and all hooked up and already tested before it was sent out. And my works cited. And this is the HS1, and this is my senior technical project. And thank you for your time.